Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good morning, good afternoon, and good evening. Welcome, everyone. It's my pleasure to introduce my friend and colleague, Professor Rose Yu, who's in the Computer Science Department here at UC San Diego. Rose has worked on a number of scientific applications of machine learning, including fusion power and climate science, and holds a number of awards. I won't list them all, but to name a few, the Presidential Early Career Award, an NSF Career Award, DARPA Young Career Award. So it's really a pleasure to have her with us to talk about most recent research on grounding foundation models. So whenever you're ready, Rose, the floor is yours, and we're looking forward to hearing about your work.
Great. Thank you so much, Duncan, for the kind introduction. I'm an associate professor in the computer science department. Today, I'm happy to share some of our work on grounding foundation models for automated climate science. I should mention a lot of the work is actually in collaboration with Duncan. We have built a really great synergy between computer science and climate science in UC San Diego. There's a lot of excitement around this concept of AI co-scientists. For example, in OpenAI recently released a deep research where you can just ask a simple question, and then you're really trying to understand what the question is about and gather a lot of insights across different locations, across industries, and all these tools to help you understand the question. You can also, recently, Google also released this scientist called AI co-scientist, where it helps you from hypothesis generation to experimental design to coming up with a hypothesis analysis for a particular question. Most recently, Anthropic released this agent called Cloud for Life Science, where you can utilize a lot of the knowledge in biomedical domain on the internet and then synthesize knowledge into structured question answers. It can help life scientists to figure out what direction to dive deep into and what type of data they should look into, and in a much more easily accessible portal. So all this technology behind the AI co-scientist is called the foundation models. So the concept foundation model means these models that were trained in a single modality, but then can be used to solve tasks in a variety of domain. So for example, text to text, image to text, text to video, all these tasks that used to be solved by separate models now can be solved by a single model, which is the foundation model. And here is the Stanford AI Index report showing the foundation model performance compared to human baselines. Each solid line here represents the performance on a particular benchmark. For example, the PhD level science questions, the multimodal understanding, competition level math. As you can see, since year 2012 to the year now, the performance on these benchmarks has skyrocketed, some of them even surpassing human baselines. But despite the success in foundation models, they can also have failure modes. For example, this foundation model released by OpenAI called Sora, which is the state-of-the-art testy video generation model. Here, if we prompt the model with a question, a telecasting, a sports telecasting of a gymnastic performing an aerial flip during a floor routine, then the model will try to synthesize the knowledge of the physical world and generate a high resolution video. And this is what the model generates. So clearly, these videos are not physically helpful. This may be okay for entertainment purposes, but when it comes to scientific applications, such mistakes have a much higher stake. So therefore, the theme of our research as a group is how to ground these foundation models with laws of physics, a theme that we have spearheaded in the past few years called physics-guided deep learning. As we know, deep learning is the workforce behind modern AI, and deep learning is a type of method that is based on very expensive data and are extremely efficient to compute. There are tools in deep learning that utilizes neural networks, graphical models to perform efficient inference. However, they often lack a framework of physical reasoning, and they're black box models, which are very difficult to interpret. They also require a huge amount of data to learn. So in science and engineering applications, obtaining the data itself is quite expensive. However, in science and engineering, the traditional framework of modeling and reasoning is based on first principles, a field that is really stemmed from physical science. So in physics, we have very rich domain knowledge, and then we can build very easy to understand models. Even with a few examples, we can build highly accurate models. They enjoy low sample complexity. However, the downside of existing physics-based modeling is that they often rely on very rigid assumptions about the data, and they can be very expensive to compute, especially for high resolution, highly complex dynamical systems. And they also generalize poorly to a new system. For example, for a new dynamical system with a slightly different initial and boundary condition, we would have to design a different type of physics-based model. But you can see here, the learning-based approaches and physics-based modeling approaches share complementary strengths. Wouldn't it be great if we can combine the strengths of both worlds so that we can have both low sample complexity, efficient computation, and physical consistency in the predictions? Eventually, we can build the AI and science applications that are really trustworthy by our scientists. So I wrote a survey article together with my student, published at PNAS last year, called Learning Dynamical Systems from Data, where we provide a comprehensive introduction to physics-guided deep learning. I encourage you to check it out and feel free to send us any feedback that you might have. So following this framework, we have made a lot of progress in a variety of disciplines. For example, we have developed models that can accelerate complex turbulence simulation. This is an example of Rayleigh-Bénard convection, which results from the cold fluid in the top interacting with the bottom fluid, the hot fluid in the bottom, which create very intricate turbulent behavior. To simulate this type of turbulence usually takes several months. The idea of building surrogate models is to develop deep neural networks that can emulate the dynamics of this type of turbulence. But the key technical challenge is how do we build an emulator that can also respect the underlying physical laws? We have developed a hybrid deep learning models that integrate techniques from computational fluid dynamics with neural networks. Our model TFNet, or turbulent flow net, can accurately capture the energy spectrum of the predicted fluids compared to the ground truth, closely following what's called the Kolmogorov energy spectrum, but at the same time, much faster than existing numerical-based methods. And for three-dimensional turbulence, we were able to achieve 3 orders of magnitude speed up compared to existing numerical-based simulation models. We also worked with CDC to accelerate their modeling of epidemic dynamics. So similar to turbulence modeling, in epidemic dynamic modeling, we also have very complex physics-based simulators that models the disease transmission from county to county. In there, we have to account for the intricate transmission patterns through different transportation behavior in the air, in ground transportation, and different policies such as school closure, disease variants, etc. So to run such simulation and generate a hypothetical scenario usually requires scans through thousands of parameters and takes several weeks to generate a single scenario. Obviously, it's not enough to meet the wartime need for real-time decision-making in epidemic modeling and prevention. We worked closely with CDC during the years of COVID, and now also working with them for seasonal flu modeling to develop a digital twin of the disease models, such that our neural network digital twin can produce the future trajectories much faster than traditional physics-based models. What's special about this model is that we use the Bayesian active learning strategy. So instead of pre-generating the training data a priori, which takes a lot of time, we use a simulator in a loop approach. So we start with a small amount of training data, train a model to generate uncertainty. Use uncertainty, we can then gauge where should we sample more to gather more training data. This kind of iterative updating schedule reduces the number of examples needed to train the surrogate by 68%. And then compared to the ground truth, which is the simulation from physics-based simulators, our model can generate very accurate predictions across different compartments, including infectious symptomatic, infectious asymptomatic, etc. And not only the mean closely matches with the ground truth, but also the confidence intervals of this prediction closely mimicking the uncertainty of the underlying physics. More importantly, this model, because it's a deep neural network-based model, it can accelerate what used to take 1 week now to 1 hour. Across 40 also national teams in the US, our team was ranked #1 for its forecasting uncertainty. As I mentioned, we work closely with CDC now to accelerate the modeling of seasonal flu and inform decision-making on vaccine distributions. We also work with scientists in chemical science field to design neurogenerative models that can generate small molecules. And this is the field called de novo drug design. Before, people would have to sift through several hundred millions of possibilities to figure out the combination of different molecules that could be effective for a particular protein target. However, with the rise of generative model, we can then directly optimize in an embedded continuous latent space to find the molecules that have the optimum property, including log-P, sensitizability, drug necklace, and binding affinity. What's special about our generative model is we combine the data-driven neural networks with physics-based simulations for simulating molecular dynamics interactions that can actually capture the binding affinity between a small molecule ligand and the protein target. This leads to 40 to 50 times time reduction compared to state-of-the-art reinforcement learning-based algorithms. And some of the compounds generated by this generative model have even better binding affinity than tamoxifen and raloxifene, those drugs available on the market for human estrogen receptor, a cancer target. We're actually working with experimentalists to test some of these approaches and hopefully eventually bring these algorithms into use. We also integrate a variety of physics-based simulations with a range with a trade-off of accuracy and computation. So we have cheap molecular docking-based simulators, but they're not accurate. On the other hand, we have binding free energy-based calculation that is much more accurate, but takes a long time to simulate. So we build multi-fidelity generative models that can integrate this range of simulators into a data-driven deep learning framework to generate a molecule that can synthesize knowledge across different physics-based simulators. So these are some examples of application from physics-guided deep learning. And when you come to climate science, which is the topic today, I would say there's a lot of unique challenges that brought by climate science to AI. For example, we have to respect the laws of physics in modeling climate because climate science is essentially describing the physical process and the energy transfer from the land to the ocean to the atmosphere. And there's a huge amount of uncertainty in climate models and also the observational data. As you can see, if we project the climate progression into the future years, the cone of uncertainty starts to grow really quickly. So how can we design AI models that can faithfully respect such uncertainty in both the models and the data is a major question. Another challenge that is very unique in AI is distribution shift. And we know that in climate science, the distribution is always shifting just because the mean of for example, global temperature is slightly increasing every year. And therefore, the data that was trained for a particular AI model will be quite different from the scenarios that it will be tested on. And a challenge called distribution shift. Last but not least, there is this question of causality. So we always want to understand the question of why and figuring out just from observational data, why is there a sudden heat wave in Texas or what is causing that? So unfortunately, we cannot do interventions such like the medical domain. So we have to rely on assumptions and models to derive causal structures from data. Now, with the rise of foundation models, we have to rethink about these challenges brought by climate science to AI and how we can utilize the general framework of foundation model to address these challenges using a unified framework. So that brought us to the topic of grounding. The grounding means we need to utilize external information or knowledge base or simulators to guide the model's behavior so that they can align with our expectations. So for climate science, we want to ground the foundation models with laws of physics, with causality, with uncertainty, and to such that they can produce much more scientifically reliable predictions. And when we think about this topic, grounding foundation models, there are a lot of techniques that have been developed before. For example, RLHF stands for reinforcement learning with human feedback, which means that in this case, the model needs to learn a reward model from user interaction and use this reward model to align the behavior of foundation models. And there is also this technique called RAG, which is retrieval augmented generation. So we can retrieve, for example, from a large amount of documents and scientific research articles to ground the model's behavior so that the model can have less hallucination. There's also this technique called grounded supervision, which means we will fine-tune the model with paired supervised data so that this type of supervised label data can slightly steer the model's behavior toward the desired direction. And of course, there's another technique called joint embedding, famously a technique called CLIP, which is learning unsupervised paired embeddings of data from different modalities. In here, we're aligning the embeddings of images and text so that hopefully for downstream applications, the model is much more well behaved in this multimodal space. But when we think about climate science, all of these techniques break down. For example, if we want to use the human experts to provide our reward function, that would mean we have to constantly ask our climate science experts for their feedback, which is very expensive. And we know RAG is very brutal and not reliable for high dimensional data. When it comes to grounded supervision, which required paired data that is labeled. This doesn't exist for climate science. We don't have paired data in both text format and numerical simulation that is already well labeled. And when it comes to joint embeddings, there's just no such data that has perfect matching similar to image captioning for climate science. So therefore, we have to think about a different paradigm to ground foundation model for climate science. So the way we think about it is, say, suppose we have foundation models that include diffusion models and large language models. And in the physical universe, we have differential equations and scientific simulations. So first, we will use these differential equations to build dynamics-informed foundation models, such as diffusion models. And then these dynamics-informed diffusion models can serve as fast emulators for scientific simulations. And then these scientific simulations can be used as efficient tools for large language model agents. And eventually, we can reach to the ideal world of trustworthy scientific foundation models. So I'll first talk about how we can use differential equations and dynamics to inform the design of foundation models, a technique we call diffusion, a dynamics-informed diffusion model. As you know, diffusion model is this class of generative model that gradually degrade the data with noise and then revert that process to generate data from noise. What typically is used in diffusion model is people would add a Gaussian noise at every step of the diffusion process and then revert that process to synthesize data from noise. However, this process does not account for the underlying dynamics in the data. And when it comes to high-dimensional climate simulations, it can be very slow to simulate because we have to add noise at every step of the dynamics diffusion process. So we devised this technique called diffusion, where we proposed a temporal interpolator that can be learned from data. This temporal interpolator gradually degrade the data using dynamics from the data so that we can save the intermediate steps in diffusion to accelerate the sampling time. And this technique can reduce the computational complexity with respect to memory footprint, data efficiency, and the number of diffusion steps. It naturally captures the long-range dependencies and can generate probabilistic ensembles. This animation shows how diffusion iteratively perform interpolation, which is degradation of data, and forecasting, which is the denoising step to generate data from noise. And then we can also show that diffusion, despite the learning from data, is actually implicitly modeling the solution to an ordinary differential equation, whereas the classic paradigm in DDIM models a different dynamics. So therefore, they lead to very different solutions. We showed some initial results on emulating the dynamics of fluid turbulence. So in this case, we're trying to forecast the velocity field of Navier-Stokes equations. And the top one showed the ground truth, the middle one is a baseline, and the bottom one is the samples from our model, diffusion. We also measured the different metrics quantitatively for sea surface temperature and Navier-Stokes equation forecasting. The metrics include CRPS, which is a probabilistic metric. Mean MSE is a deterministic metric. SSR is a forecasting skill ratio. So the better, closer to 1, the better, and the runtime. So as we can see, the MCVD, which is the baseline on top of diffusion, is what was used for Sora to generate videos with a diffusion model. So our model diffusion have very competitive performances in terms of CRPS and MSE, but it's much faster than existing classic diffusion-based methods like MCVD. So based on this technique of diffusion, we extended it to model the global climate. In this case, we need to account for the spherical geometry of the Earth. So we simply replace the backbone in the original diffusion model of the UNet to a spherical Fourier neural operator. So a spherical neural Fourier uses the Fourier basis to model the 3D geometry of the Earth. And then the sampling techniques is exactly the same as what I described before, that couples the dynamics of the diffusion process with the dynamics of the data. This paper got the Best Paper Award at ICML, one of our leading conferences. And in collaboration with LNT Institute in AI, we actually developed the very first stable probabilistic global climate emulator that is able to speed up the simulation of global climate modeling from 6 months to 1 week. We can generate stable rollouts at 6-hour resolution for 100 years. Compared to the previous baseline developed by AI2, our method achieved a 70% improvement over the state-of-art emulators, and it can also generate probabilistic ensembles to give us uncertainty of the climate projection. So now we have a very fast emulator. The question next is, how do we use these emulators for large language models and scientific tools? So we developed this technique called adapting while learning, which allows the LLM agent to choose when to use these emulators. As I mentioned, these emulators or these tools in scientific field are quite expensive. Even though we have significantly speed up the climate simulation from months to weeks, still getting one feedback from the emulator takes several weeks. And running these tools is quite different from the classic tools in LLM agents, such as web browsing. These tools are costly, so therefore we have to be cautious about when to use tool and when to use the internal memory of the agent so that we can trade off between performance and computation. The first question is that how do we interface the simulation tools that we have, which is highly numerical, with large language model agent, which reasons in natural language? So to interface with scientific simulation, we use a template-based approaches. For example, here we looked at examples of physics-based simulations in 4 different domains: the Mojuko-based physics simulation, and partial differential equation simulation, the climate modeling simulation, and epidemiology simulation. So for each simulation, they have a set of input and output parameters. So we could use these input parameters as blanks in the question and generate a set of template that ask in the domain where we can simulate data. For example, for climate, we can ask how much will the temperature of Chicago in 2018 under scenario blank change if the emission of carbon dioxide is decreased by certain amount, which is blank. So these blanks can be filled in with the input to simulation. We can also ask open-ended questions. For example, in climate, we can ask the LLM agent to design a maritime route from Singapore to Dubai that increases the SO2 level by certain amount blank. And then we can also specify that this proposal should have at least an impact on global temperature production under certain scenario blank. So then we can use these templates to generate a lot of paired data of input question and output answer from the simulation. Then we can use these paired question answers data to fine-tune our foundation model, the LLM agent, so that these LLM agents become much more adapted to answer this type of scientific questions. To make sure that the model knows when to use this tool instead of always relying on using the simulator, we have 2 stages of learning. The first stage is called word knowledge learning. So essentially, it's self-supervised fine-tuning. So we use the template-generated question answers to fine-tune the model. So for closed questions, we will directly use supervised fine-tuning. For open-ended questions, we could use preference-based optimization so that we can give the preference of 2 pairs of answers. And this kind of word knowledge learning, the model already knows the knowledge in the simulator. So therefore, the next stage is tool usage adaptation. So in this case, the model will evaluate the difficulty of the question. If the question is hard, then the model will try to use a simulator as tool. If the model is easy, then the agent will try to answer the question directly from its own memory. In this way, saving a lot of the cost of running expensive numerical simulations. So with this type of two-stage approach, we can see that we slightly change the knowledge scope of the agent. Originally, the red ones represent the hard problems, and the blue ones represent the easy problems. And the vertical separation indicates when to use tool and when to not use tool. So through the first stage, word knowledge learning, we can see that what was used to be hard for the agent can now be easy because the model now has distilled the knowledge from the simulator using self-supervised fine-tuning. And through tool usage adaptation, we can see that what was used in hard problems, the model will tend to use the tools a lot, but then for easy problems, the model will now try to answer the question from its own internal memory. So we compared this strategy with some of the frontier models across 4 different physics-based simulations. Cloud, GPT-4, and the base model is what we used to fine-tune our model upon. And the base Llama AB model has very poor performance to start with. But then with our fine-tuning strategy, adapting while learning, we can significantly improve the performance, surpassing the performance of some of the frontier models. What's interesting here is I want you to pay attention to the yellow bar, which is forcing the model to use tool all the time. So in this case, we still pay a lot of cost to run the simulations and instantiating the tool, but the model become over-reliant on using these tools and have a trouble generalizing to new problems. And this highlights the importance to be adaptive, where the model only needs to use scientific tools when necessary. So that also helps with the model to generalize to new scenarios. So I led a project from DAPA called Genie, which is a generative foundation model for automated climate science, and together with Duncan and several other colleagues. So in this project, the vision is trying to integrate multimodal data from numerical climate simulation and observations with rich text data from research articles, climate reports, and textbooks. And once the model is trained, we can fine-tune it for a variety of tasks, including forecasting, causal inference, and scenario creation. To ground the model with scientific knowledge in climate science, we proposed to integrate laws of physics, prediction uncertainty, and unpunctuated learning to mitigate hallucination in climate science. Lately, we developed this agentic framework called Zephyrus. It's an agentic framework for weather science. So specifically, given an inquiry, the LLM-based agent, Zephyrus, writes a code block, which is then sent to the code execution server. The server orchestrates several tools to execute the code block and returns the execution results. In this agentic framework, we integrate the tools, including WeatherBench 2 dataset, the global climate model emulator, the forecaster for weather forecaster, and geolocator that can locate a particular latitude and longitude on the globe given textual descriptions. Then the agent either decides to execute more code to refine its output or respond back to the user. So in this paper, which is to be presented at NeurIPS workshop on scaling agent environment for agent, we have made 2 major contributions. The first one is this agentic environment that can efficiently execute multiple tools in parallel. So we spin off a pool of workers, and these workers can call this set of tools available and send the code back to the Zephyrus agent to decide what to iterate next. The second contribution is this semi-synthetic benchmark that we created for the agentic framework. So before this work, there's no benchmark available for testing agentic performances in climate and weather science. So here we take the wetted text corpus and use an extraction agent to extract simple, verifiable claims. These simple and verifiable claims can be used by LLMs as reusable templates, similarly to what I described in the previous framework. And we can verify these templates easily because there are only a few of them. So using the template and couple that with data, we can then generate a large number of synthetic data sets. And this synthetic data set can be both used for fine-tuning the agent and also for evaluation. So we released the Zephyrus benchmark, which is for evaluation. And in this case, we have 3 categories of tasks from easy to hard. And each task has about 2,000 questions in the benchmark. As an initial evaluation, we showed that with the agentic framework, the Zephyrus agent can significantly outperform the text-only LLMs, which is in green. So across different backbone models from GPT-5 to Gemini to GPT-OSS, whenever we add the Zephyrus agentic framework, we can boost the performance by 20 to 30%. So finally, I'll show you a quick demo of this agent in action. So essentially, this is an user interface in natural language where we can ask a simple question and the model will load all the tools in the backend and then interact with you in natural language. So for example, we can ask the model simple questions like, please plot a linear regression of average annual surface temperature in Japan. And the model will understand the question, start to generate executables in code, and then instantiate the code execution server in the backend to give you this visualization of the plot, and well as a natural language response, both of which can be used for scientific analysis. We can also analyze the code generated in this answer to further verify the accurateness of the answer. We can also produce region-grounded answers. So we select a region and ask a question. Please provide a meteorological report for conditions in this region on 2022, 7 and 5. And then, as you can see, the model starts generating the code and execute this code to produce a human-readable report with a very rich text and numerical information. We can also ask the model to forecast the average wind speed in France in July 2022, and would ask what is the actual experience, the wind speed. So the model will now use the forecasting tool and the simulation tool available to generate the 7-day forecast for the wind speed, and then also compare that with the actual experienced wind speed in France. We can also ask the model to generate simulations and understand what date in the region experienced the lowest surface temperature in 2020. So the model will run the simulation in the backend and show the lowest simulation in. We were trying to add more tools and agentic abilities to this Genie so that it can solve more complicated questions and provide more value to climate and weather scientists and decision makers in policy space. So hopefully, I have showed you some examples of how computing and AI can transform our scientific discovery process. Mostly, I focused on the applications to climate science, but I also alluded to applications in other scientific fields from epidemiology to drug design. I would say that science represents an exciting frontier for AI, and AI represent the most accelerating new instruments in the hands of scientists. We can imagine a future where our scientists and AI agents work side by side from hypothesis generation to data analysis to experimental design and causal analysis. AI will co-pilot with scientists at every stage of scientific process. Scientists, on the other hand, will provide the necessary guidance to ensure that AI is conforming to the scientific truth. So with that, I'll just conclude my talk. You can find most of what I talked about today on my website or follow me on social media to see the latest update from our group. And I would like to thank the funding agencies for supporting this work. Thank you very much.
Wonderful. Thank you so much, Rose. It was a great overview. Lots of interesting things to talk about. I guess, I mean,
Thank
just
you.
perhaps starting at the end, with your vision for how you see these AI kind of co-scientists working with scientists. Is that how do you see as these foundation models, look to get bigger, and so I'm thinking of like ChatGPT and Gemini and so on. Where do you see the role for these kind of more focused co-scientists as opposed to the large foundation models? And there's an interesting kind of trade-off, I guess, between domain knowledge and broader knowledge. And at some point, will these just be subsumed with GPT-6, or do you think there's always a place for these kind of more domain-specific tools?
Yeah, that's a great question. So I think there's always a place for these specialized models because, as we know, the general purpose models, they are essentially pre-trained on internet knowledge. So then, knowledge itself is very noisy, right, on the internet, so that we need higher quality curation of the data and the tool usage for specialized domains, and such that their answers and the decisions made by these foundation model are much more trustworthy than general purpose models. The other aspect is this phenomenon called catastrophic forgetting. Obviously, there's the knowledge and information that can conflict with each other on the internet. And then when the model is trained with such a huge amount of data across different domains, then one can imagine catastrophic forgetting to happen in these general purpose models. So when it comes to specialized models, because we can then separate specific use cases and tasks for a particular domain, so then we have less tendency to forget in certain skills.
Okay, yeah, that makes sense. Yeah.
Coming in with the question, very nice talk. I mean, somehow retirement as a climate scientist feels slightly a little bit closer after your talk, but that's a slightly boring separate question. No, coming a little bit, the obvious question to ask is a little bit about sort of, trustworthiness and explainability with some of these questions. So with the demo there, when you asked the model, what was the simulation, what were the conditions for real over France for the time period? How safe is your specific model or models in general against just making up things at this point? Because quite often models would give you an answer even though they may not have the data or not have a lot of uncertainty. How do you build that in that we really can trust the results?
Yeah, so actually we thought a lot about that particular question in this project. So one is that we use the agentic framework, which means that the model will instantiate tools given a question. And then so the answers it given is actually the result of executing a code block. So if the question asked about something that was not in the tool pool, like the pool of tools, then the model will not be able to generate the code and call that tool. So then the model will say, well, I don't know because that tool that you're asking for is not available in the tool set. So instead of hallucinating from random knowledge, the other thing that we emphasize a lot in this project of Genie is to calibrate uncertainty of models prediction. So specifically, we have developed a set of tools that can look at uncertainty, the confidence of the model's prediction itself. So essentially, when we generate the forecast for a large language model, we can also produce the confidence intervals of that forecast. This obviously requires calibration techniques on the natural language side, not only the numerical weather forecast, because there's uncertainty associated with using the tools itself, the uncertainty from the data, and also the uncertainty from the LLM agent to execute the tools and then produce the answers for you. So we have to compound all this uncertainty together to produce a well-calibrated answer.
Okay, thank you. There's actually maybe a good question to follow up on. That's from Gavin Schmidt from NASA, who basically asked you, do we think that 50% of corrected answers on the benchmark questions is even close to be sufficient?
Oh, and yeah, that's a very interesting question. So I personally don't think so. I mean, 50% is right. Let me go back to this result. So 50% on this benchmark is definitely not enough. That's why this benchmark itself is valuable. But if we create a benchmark that all the models can already achieve 99%, that means the benchmark itself is not challenging enough. It's not going to inspire development on the model and methodology side. As we can see here, the weather question answer tasks here that we have listed that has different levels from easy question to hard question. The hard questions include some of the causal analysis and counterfactual questions. The easy questions is more like retrieval and statistical analysis tasks. So across all these different categories of questions, the models don't do very well, especially in hard category of questions. That shows there's a lot of potential for us to improve both the algorithm, the workflow, and then the general framework for using foundation models for solving weather and climate tasks.
Thanks.
Yeah, I think that's a good point. There's another question from William Locke asking if there's any work you're aware of interpreting the internal representations of deep learning models that are trained on physical data. So I guess this is kind of getting at embeddings, but asking in particular in their case, looking at inferring phenology data from satellite data about vegetation. So can we kind of, I guess, inspect models that are trained on a lot of physical data and infer new kind of physical insights from those? Are there any examples you're aware of that?
Yeah, so like we have, I guess there are two different branches of work that touches upon this question. So one is this area called interpretable deep learning or interpretable machine learning. So they're trying to take a trained model and then poke inside in the model and try to understand what could be correlated with the predictions, right? So there are techniques, for example, like mechanistic interpretation, where people look at sparsified activations of neural networks. There's also techniques called the Shapley score or the line method that looks at the decision boundaries of a neural network when it comes to high-dimensional data. But these interpretable machine learning or interpretable deep learning methods, they're merely creating correlation. Some people also use attention maps to look at what are the features that are most predictive of certain output. But these correlations are very fragile, and even though they are interesting to look at, they can often lead to misinterpretation of underlying physical mechanism. So in our group, we don't do much on that space. On the other hand, we look a lot on the causal analysis of the model. So we can then use deep learning models to directly predict the causal graph from the data. So then once we take out the latent variables in the model, they directly map to the edges and nodes in the causal graph, so we can draw causal conclusions. Obviously, the challenge there is how can we make sure that it's actually causality, not correlation. So we have to rely on certain assumptions of latent confounders in our data and utilize some of the recent development in causal representation learning in deep neural network community. So that's a very different line of research that we do in the lab, but we haven't talked about that in this talk. The third one that I just thought about is sometimes we also wanted to use models to directly extract equations or the laws of physics from data. So yeah, we have some work in our group, and together with also others work on this idea of AI physicists, right? So you can use symbolic regression or sparse regression techniques to directly extract equations from data. And then you can use equations for downstream interpretation. So the equations are in symbolic form. That's much more interpretable.
Yeah, no, it's exciting. And that link to then having some agent that can interpret or reason about that data and the experiments and set up next experiments. It's very exciting.
Exactly.
So I have a more general question, and that's much of the work you've showed what was sort of a little bit on the interface between LLMs and sort of often gridded data, so sort of model output data, physical simulators, and so on. There's a whole sort of different strand of foundation models where people primarily think about sort of pure observation-driven multimodal foundation models with all different observations. It's a bit complementary. So one question I had is a little bit, how do you see those sort of coming together at some point? And then also, if you had thought in the sort of pure observation-driven work, it's not maybe as obvious how you would ingest a physical constraint as in something that's just a much more structured model like a simulator. I wondered if you had a little bit about thoughts about embedding the physical constraints when you really just purely learn from quite sparse observations often.
Yeah, I think that's like some work that we did before, not necessarily in this work. So the idea of embedding physical constraints in deep networks for pure observational data, that could include techniques like encoding symmetry in the construction of neural networks. So we've done a bunch of work on that. And then we can show this symmetry-aware neural network can have much better generalization to uncertain scenarios than the baselines without symmetry. We have also integrated, laws of physics as regularizers in a loss function to steer the model's behavior towards more physically constrained output space. I guess the reason we're looking at this new framework of integrating large language models with scientific and numerical data is we felt that the reasoning ability of these large language models in human language is progressing extremely quickly. So we wanted to bootstrap on these skill sets that are quite unique, I would say, to large language model foundation models, and then couple that skills with the rich numerical data set that we have in weather and climate science. So a lot of the models that we developed before, and also some of the foundation model for forecasting and the interpolation or downscaling, they're purely numerical, but I feel like they could benefit from this more high-level reasoning abilities of large language model agents. And they, because they can read research articles, they can read literature in the internet, so they have much broader knowledge than just numerical simulations.
Yeah, and actually, I mean, if I may just kind of riff off that as well, Philip. I mean, one of the things I'm not sure that some of the observational kind of foundation models are that foundational at the moment. I think they're still fairly kind of focused on particular data sets. And I think, if you think about NASA, for example, and you have so many kind of sources of data from so many different streams, actually coming up with an architecture or even a set of data streams that all kind of align that would allow you to build such a thing, I think I wouldn't say it's impossible, but I think is extremely hard. Whereas actually, perhaps language is the common kind of abstraction across all those things, and so actually just being able to describe each of those things in kind of textual form could be a way of unifying them and bridging across all of them. So yeah, I don't see them as orthogonal activities, but you're right. It would be great to be able to bring in real observational data and satellite data and so on to reason about it.
Yeah, absolutely.
I wanted to just kind of take a little bit of a step back, I guess, from the detail, Rose, and just touch on some of the concerns that I think young scientists and students have about the role of these and their future in the job market, and what does a PhD even look like in 5 years' time, and just we don't have to get too deep about it, but I'm just curious if you have thoughts on or advice for young people or students watching about what they should or shouldn't think about pursuing in the
Yeah,
future.
definitely. I mean, I also get this kind of questions a lot from my students. As you know, like computer science is the discipline that is experienced the disruption the most from the LLM, programming and the progress in foundation models. So I would say that the skill sets that we need to develop these days are very different from the skill sets we need to develop before. Right? So for computer science students, before you would learn programming, but now probably programming is not the most important skill set that we should develop, but rather the ability to debug, the ability to judge, the ability to understand the reasoning process of these LLM agents is probably more important. Of course, you have to know programming in order to figure out the bugs or understand the correctness of this code. So, but then the nitty-bitty of writing some highly complex engineering software probably is no longer the necessary skills for computer science students. And then for science students, like students in climate science and other scientific field, I would say that we really have to bridge the gap between computers, the computational field and the scientific field. So a lot of students, they are also learning skill sets outside of their traditional disciplines. So, AI and computing, they are kind of the necessary tools everybody should know about, if not mastering about. Then you should at least know how to utilize them and accelerate your own research discipline. And then, of course, I think the future of AI and science is not necessarily one replacing the other, but rather this picture that I showed is a co-piloting situation. So you need to have the right skill set to judge whether the AI is doing the right thing. Of course, you have to understand your own scientific field well enough to say this is the right principles or this is the right question to ask in your scientific field. So AI is great doing a lot of the legwork for writing code, doing repetitive experiments, but still it's quite lacking in this intrinsic human curiosity in the world and asking the right question for the scientific inquiry. And that's the role that our scientists can play and our students can play to think about what is the right question to ask that can lead us to the next generation of discovery.
Wonderful. No, that's a really nice point to end it on. I think that was a good overview and a good call to arms, hopefully on a positive note. So, unless there's anything else from you, Philip?
No, I think, as you say, this was exactly good closing words for next generation and ourselves.
Fantastic. All right.
Thank you so much.
Well, no, thank you for joining us, and thanks for the fantastic talk. So we'll be back again in 2 weeks for our AI for Good seminar. So we'll see you then. Thanks again, Rose.
Thank you, Duncan and Philip.
See you next time.
Bye.
Bye.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.